Right. So we were discussing this particular precision rectifier and what happens when Vn goes positive and when Vn goes negative. What I was trying to clarify in the diagram was that when Vn goes positive, dP, this diode, let's put it on here. Oops, let me go backwards here. Right. When Vn is positive, dP, if Vn is positive, dP is on and Dn is off. So with dP on, I had drawn the circuit here to show upstairs with dP on, you have a short circuit from the input to the output, from the output to the input of the op-amp, and this is what the equivalent circuit looks like. And then when you put Vn as negative, this diode is on and dP is off. So this one acts like a short circuit, which creates an equivalent circuit like what we have down here. And then I was explaining using Vn plus and Vn minus. But unfortunately, that leads to a little more confusion than I wanted. So what I'm going to do is to redraw this and put instead something like minus V here. So on this, to put like minus V here and plus V here, or something of that nature, and see what the actual output of the answer is. So I'll redraw the circuit and record a small explanation of it again, so that to try and clarify what's happening, and try to also to explain it in the context of the fact that these are two non-inverting amplifiers. So to explain it in that context a little bit, okay? So I will put up that later on today. I'll try to record that, and hopefully by tomorrow sometime you'll have a little explanation now with a better diagram that clarifies it. All right? Fair enough? So give me some feedback if that's the case. So,
yeah. Sounds good, sir.
All right. So where were we? We were discussing, I think the last time, so we were talking about this one. Then we spoke about this is a half wave, and in reviewing, we also did the full wave version. All right. And then now we have, we'll talk a little bit today about these waveform generator circuits, which are the second set of operational amplifier applications. Okay. So let me just stop there and share. That would be operational amplifier application, this one. Okay. All right. Right. So one of among them, the hundreds of applications of op-amps are the ability to set up the op-amp to generate waveforms. And waveforms, we saw part of the waveforms that we looked at already. We could do square waves. Right? Remember the op-amp. The op-amp is a bipolar device. You can operate it, is usually to operate between plus and minus VCC, but you can also design an op-amp to work on either plus VCC or minus VCC supplies. And there are also op-amps that can work on a single-ended supply, in which case the waveform for a single-ended supply would go from 0 to plus whatever is the maximum output of the op-amp. We also saw that you can make the op-amp generate signals like this, sinusoids. And those were by putting these RC networks in the feedback. And we spoke about things like the Barkhausen criterion and so on, so we can get these sort of sinusoidal waveforms being generated. And then we also now in the position to create waveforms looking like this, like triangle waves and also ramps, which would be a single waveform that either does this and stops or does this and stop. All right. And the way to get a ramp to work is to remember something that we discussed elsewhere, which is that if you take a step function and you integrate it, remember what an integral is, right? And we saw this in signals, but an integral of fx, right, is really the area under fx, right? So if I were to integrate a step, this area here, as you keep moving this, integrate this between naught and some time x, right? Is x here. So as x keeps moving along, this area keeps getting bigger and bigger uniformly. So in fact, when you integrate a step, what you get, the answer, which is the area here, it starts at 0 and it uniformly increases as x gets bigger. So when you integrate a step, what you get is a signal looking like this, which is a ramp, right? Usually a one-to-one slope if it is a unit step, yeah? So therefore, if I know how to generate steps already electronically, if I take a normal battery or a cell, put it to a switch, and then send it to a circuit, right? If the switch has, let's say, a little resistor keeping the output at 0, when I put the battery on, this point is going to go up to whatever the battery voltage is. So I could create a step very easily. So electronically creating a step is just basically connecting a switch to VCC. And if I have a way of integrating that step, then I could create a ramp. And we know that one of the applications of an op-amp is to create something called an integrator circuit. And you create an integrator circuit by taking the feedback resistor of the op-amp, the normal inverting op-amp, and instead of the feedback resistor, you put a capacitor. And once you put a capacitor in there, now, if you follow the current, the voltage and current behavior through the capacitor, then eventually you get that the voltage at the output of the capacitor of the device is the integral of the voltage. In fact, the voltage across the capacitor is the integral of the input voltage, and the components R and C determine how fast you're able to do what do you call it? The integration itself. If you use 1 microfarad and 1 megohm, then it turns out that the output is minus T, which is a negative going ramp whose slope is 1 minus 1. And if you plot it right here, which is what I did, you put the circuit and you simulate the circuit, you could see that once you put this step voltage in, which would be right here, so you find a way to increase the step. As I said, a simple switch would do. As the step goes in, as soon as you put that, the output of the op-amp starts to decrease very linearly until it moves from plus VSAT, whatever is the saturated output of the op-amp, to negative VSAT. The thing about it is that in most cases, to try to prevent it, because the op-amp open loop gain is so big and little bias currents, even if you don't have anything inside of here, there's still a little bit of bias current going inside of here. That is enough to start the ramp operation going. So usually what you do is that you in a practical circuit of this nature, you would have a switch across here, and you keep the switch closed when the circuit is not to ramp. When you're ready to ramp, you open it up and then put the input voltage. All right, and then you get the ramp behavior happening. So you could get this now. You could, whatever R and C is, you could get this as short or as what do you call it, as shallow as you want by determining the value of C, by you picking the value of C and R. Usually for a typical op amp like a 741, this normally is about the maximum you could go for the input resistance, about a megohm. Here, you could probably get up to maybe 10 microfarads. Sometimes you could try 100 microfarads here, but usually you wouldn't, the op amp at that stage, you know, the leakage currents and the currents through the resistor and the capacitor are sort of approaching the current that the amplifier requires to bias, and it doesn't work too well. I think I mentioned that the last time. All right. So this is a way of generating a single ramp. Right. There are a number of applications for this. For instance, oscilloscopes. They use ramp signals to trace the signal out. Right. So they not the digital scopes that you're seeing, but the older scopes in the lab to move to make the trace move across the screen. The voltage on the that is moving in the if like this, a time-based voltage to sweep is our ramp type signal, and you can control that by the knobs on the scope. So that's just one application, right? Cameras use it when they're scanning the pixels across in the sensor behind the lens and so on. They use ramp signals repeatedly in that sort of application. All right. So that's one sort of application that we saw, right? And it's fairly easy to figure out how to hit. Notice this bit here. So you need to know this always. Whenever you pick on op amp, if you're supplying it at plus or minus VCC, the op amp does not generally go to that. It goes to a close output, which is its saturated output. In most op amps, this is like about less than or equal to maybe 1.5 to 2 volts less than VCC. There are new op amps and specialized op amps that give you what they call rail-to-rail output, which means that the output will go at plus or minus VCC. But if you're taking a regular op amp like a 741 op amp or a commercial LM308, those kind of things that you met already, if you're doing that, generally if VCC is like plus or minus 15 volts, the saturated voltage may well be like plus or minus 12. That's about as good as you can get, right? Don't try to aim for anything more. So you have to bear that in mind. This is part of the sort of selection process when you're dealing with electronic components. Right. So the other one now is that if we could find, the thing about it is that if I put the op amp like this, and at this point in time, if I had sent the VCC back down, in other words, if after I've put this step on, I now ground the input, then the op amp now is going to ramp the next circuit. There's a negative going step. So it's going to integrate that and it's going to do this. And if, when it does this, and it will saturate, if I were to, at that point in time, right, the signal is here. If I were to do it and give it a positive going step now, it's going to do this. This now, the series of ramps creates a triangular wave signal. All right, and those are also signals that are very useful in certain types of applications as well. And also, if you remember, just showing this back from some other things, if you remember when we did in signals, the Fourier series, you remember that the square waves gave you things like odd harmonics, right? So you had a DC value and you had a perfect square wave, which is a 50% duty cycle, that you had odd harmonics, right? If you look at a triangle wave, the triangle wave also has odd harmonics, but the higher harmonics are very low. So it's very easy to go from here to a sine wave by getting rid of the odd harmonics higher up. So one application of triangle waves is really to make sine wave generators. Instead of going, you remember one of the things that we said with things like the Weinberg and so on, is that you have the Weinberg and the phase shift networks have a set of equal resistors and capacitors. And if you want to change the frequency, you have to change either all the capacitors together or all the resistors together. Or in the Weinberg, there were two. You have to change the two capacitors at the same time or the two resistors at the same time. If you can find a way of creating a triangle wave, it's very easy to change the frequency of a triangle wave, as we'll see, but one component. And then if you know that, it's really electronically easy to go from a triangular wave to a sine wave. All right, so that's one of the applications. So let's talk a little bit now about the triangle wave itself. So if I put now, as I said, what I need to do is to create an input now that is switching steps, positive going steps and negative going steps. So what kind of signal does that? A square wave. So what you do is that if you can combine a square wave generator, which is this character here, with the integrator, then what happens is now, this now is producing the steps changing positive and negative. And this one now is just simply integrating. So every time the step goes positive, you get a ramp. Every time it goes negative, you get another one, and so it's going. Right? Not drawn to scale, of course. And the output of that now, notice where you're taking the signal. The output of this is coming from here. This is the triangular wave. Here you're getting a square wave coming out. And this is a comparator with hysteresis, right? Which is a little bit of a delay, if you remember, from your physics and from your electromagnetics and so on. Hysteresis just means that if the system goes, let's say, positive to negative to positive, then when it's going back positive to negative, there's a little delay between the two, right? So right? So there's a little bit of a delay between going positive and negative. You need that so that the integrator has time to do its stuff before the switches again. That's all. And if you look at it here, so what happens? Let's assume that we start at some time B. So when this signal here, which is the ramp signal, when it crosses, we have time B here. As soon as the output of that crosses the reference voltage of the comparator, then the comparator immediately switches. So it goes from let's say negative to positive, which in turn feeds back that step to the input. And then this integrator starts discharging or charging, or however you want to look at it, until it drops as low. Remember, this now, these two here is setting up a switching voltage, a comparator voltage for it, so that at the point when the ramp voltage crosses whatever that voltage is now, it flips again and it just keeps flipping back and forth. So the net result is that you have this triangular wave, you're creating the positive going and the negative going steps. And every time you get a step, so in this case, a positive step gives me a negative slope, a negative going step gives me a positive ramp, right? Which is what the integrator does. They say. So a positive step gives me a negative slope, a negative step gives me a positive integral because of the minus sign we're using an inverting amplifier. Right? So all you have to do now, so this is what it looks like when you simulate it. What you have to do to design this is simply, first off, you have to determine what is the saturated voltage of the op-amp. Once you know the saturated voltage of the op-amp, so let's say the op-amp saturated voltage is 9. Then the trigger voltage, where it flips, in other words, the comparator voltage, when this is going to cross the reference voltage for the comparator to cause it to trip positive or negative, you determine that. So if you, as soon as you determine that, so let's say you want a 5-volt output, right? In other words, I want my output to go from plus 5 volts to minus 5 volts, right? That is going to allow me to determine this little constant here. So if this is 5 volts and this is 9, right? It means that the constant N is plus or minus 9 over 5. So once I know N now, then I can now calculate the frequency of the triangular waveform, right? And if I want, let's say 100 kilohertz, N is 9 over 5, I choose R to be, let's say they say 1 megohm, and I calculate the capacitor value. All right, or I pick a capacitor value. Let's say I have a 1 microfarad capacitor or 10 microfarad here, and I can calculate what value of R I need to make the triangular wave. It will be limited to plus or minus 5 because that is how I chose N. If I want this, if I want this to switch up plus or minus VSAT, give me a second, please. Just excuse me for 1 minute. I just have to make another call quickly. Thanks. Right. Okay, so where are we? Right, so it's a very straightforward, very, very easy thing to design and to get any sort of, what do you call it, frequency. It would typically, 100K is probably about the highest you would get with a 741 op-amp. If you start to go higher, then what happens is that this sort of, you get this kind of behavior. You get a kind of behavior looking like that. If you try to go to too high a frequency with a regular op-amp. The higher the frequency, the higher the speed the op-amp has to be because it has to integrate fairly quickly. And so you have to compensate for that. All right? All right, so where are we? So this is what, so that, right. Now the comparator with hysteresis. There is a handout. I don't know how many of you all check back and have been reading up, because each of the lectures that we did during the semester, there was a handout that provided a lot of explanation into how these things work. The comparator with hysteresis is actually based on something that you should have met in year 1. All right. And the hysteresis value basically is set by that resistor value N. But the explanation for all of these, including how the circuit works, including things like the precision rectifiers and so on, were all given in handouts that you had. I don't know, have you all checked that? Any of you all downloaded and sort of read them? You remember that?
That's from the past semester one lecture notes.
Correct. Right. The last time you took this, there were some handouts with additional. I think in all of the classes, I had some stuff marked additional reading material or something like that. And there were chapters. These notes were written up by Professor Gift from his book, and he had the handouts. He had put that there, so there was. You didn't need a textbook. In other words, you could go right there and you could read the thing. Any of you all remember check, or have any of you all been checking that?
I know what you're talking about, but for now, I will have to review it.
Right?
I better understand.
Yeah. You have to, because that's part of why I gave that, because we didn't have, I mean, one of the textbooks for this course, I'm looking for a good ebook that we could use for this. But to avoid that, what he had done is that over the period of time when he used to teach it, he had actually written up the notes. In fact, he has a book available now, and I'm trying to see if we could get it in ebook format, which would be a real useful book for you all, because it will deal with some of these things. It will also deal with things like amplifier design and so on, which we didn't cover. All right. So let me know if you have it. Some of you all, I think, may be having some issues getting onto the MySecure area. I understand there's an issue that they're trying, that Campus IT is trying to resolve. So you may have an issue getting onto the MySecure area, or maybe My e-learning. But when you do it, do go back to the semester one course shell and look for the reading material and download it and keep it, just in case they back up the shell and you no longer have it available after this period. All right. Okay. Fair enough.
So it have this link called C library. They could actually get them textbooks.
Right. So and I know through, yeah, we have a number of ebooks, which is why we didn't want to specify anything specific, but I wanted to at least have you all have material that you could go and read. A really good book, if you have access to it, if you could ever get your hand on it too, is The Art of Electronics. Right. And in fact, that may form the basis of when I'm revising this course a little bit later on to do the material, because I want to make it a little more in line with probably what the rest of the syllabus from other courses require, and also what you all will need as engineers going out. For instance, if you're in the power field and so on, you will need to know things about power electronics and the behavior of semiconductors under high currents and voltages. Now, already there's a power electronics course that we have for the people doing energy systems. There's a whole number of other applications now that are coming on stream that at least the fundamentals of how they work may be required. Right, in 5 years, half of us will be driving electric cars, and the control systems and the motor drives and all of that is pure electronics. All right, so those kind of things, knowledge of that as an engineer is becoming increasingly necessary. The other thing that we don't have time to cover much of, but we'll have to find a way to put it in, is high frequency electronics. All of the communication systems around work with analog high frequency electronic systems. And how we design for that is a lot different than low frequency audio frequency ranges and that kind of thing. All right. So it is revising. Your focus right now is to get through what we did on the past syllabus. And so I'm not, you don't have to worry about that at this point in time. I just want to make sure that you have the materials that we did cover the last time around. All right. So again, let me know if you don't have, if for some reason you can't access the shell or it's not there anymore. Let me know and I'll repost it somewhere. Okay. Right. So let me go on. So that where were we? If if I were to go back to the question paper, right? So in this question here, right? So you have, this is the same diagram inside, right? It's just labeled with RA and RB instead. So you determine the value of N, and everything is really given here. N has to do with the 10 volt supply. If you assume that one of the answers in the question here is that you have to say a little bit about what assumption you're making about the VSAT. If you assume that is a 10 volt supply and that the amplifier is able to go to plus or minus 10 volts, right? And in fact, I haven't given you any other information here. So one of the first lines you would have to tell me is to assume that the output here is able to go to plus or minus 10 volts. And then from that, now you calculate N, and N is simply 10 divided by 6, right? So you get 10, which is 1.67. And then now you remember RA and RB are related by N. So if you pick RA to be some value, then RB is N times RA. So you pick RA to be 100K, RB will be 1.6 times, 1.67 times that. And then you pick a capacitor and you calculate the resistor. And then you could sketch on the same diagram, sketch the waveform. So what you have to do is to reproduce that diagram that we had here, right? So you're going to have the output. This thing is going to go plus 10 volts, minus 10 volts, all right? And if you are dealing with the what do you call it? The actual triangle wave output is going plus, what is it? 6 minus 6, all right? And you let the output of the comparator, so the comparator would be going from 10 to minus 10 to 10 to plus 10 and so on. And the triangle wave will go within this period of time. So right? And you at the time when you have this switch inside of here, so you basically switching, you got to assume some point here. So you have the triangle wave doing that, right? It's going on. So that's what the diagram will ask you to do. Okay, fairly simple, easy 12 marks in this case, right? A very easy 12 marks, right? But you have to tell me you have to give me a little assumption that if you're using a 12 volt supply, you have to assume VSAT plus or minus VSAT equal plus or minus VCC. Tell me that, okay? All right. If not, you can, and somebody say, okay, it's a regular op-amp, so I am assuming that plus or minus VSAT is, let's say 1 volt less than that, plus or minus 9 volts, and then you do the thing, perfectly all right for me, okay? But you have to say something. Don't just draw the thing and you lose a couple of marks because you didn't tell me what the decision was. Okay, so always say what you're doing. Yeah. Right. This is I mean, it's a very, very easy course to pass. All right. So I mean, once you get over the shock of trying to remember the things for the exam itself, which is what happened the last time, it is a very easy course to pass.
Hi, sir. Is that figure the design for the triangular waveform generator?
This one?
Yeah.
No, I don't understand the question.
Okay, so it says use a 10 volt supply. Design a triangular wave generator to produce a frequency of 25 kilohertz and a peak amplitude of 6 volts.
Nice, yeah.
This is the triangular wave generator.
Yeah. Let me say it for the triangle wave generator shown in figure Q4b.
Oh, so we need to, our job is to size the capacitors and the resistors for this.
Exactly.
Okay.
So you're given the circuit, and you have to find RA, RB, R, and C, right? And as I said, you're given some information here. So you have to tell me what you're going to assume. You're either going to assume you need plus or minus VSAT in this because you need to calculate the upper threshold and the lower threshold for the triangle wave, right? So in doing that now, you have to tell me, first off, what am I assuming about this op-amp? Is this my assumption that the op-amp saturates at plus or minus 10 volts? Or am I going to say, okay, that it from my knowledge of op-amps, let's say that it could go a volt less than that, because typically VSAT is a little bit less than VCC. Tell me, it doesn't matter. But you have to say this. And once you say that, then the next step is to calculate N, which is V sat over the V upper or lower threshold, right? So 10 divided by 6, or if you have picked another value, 8 or 9 divided by 6. And then once you calculate N, once you have N, you choose a value for RA, and then you calculate RB, or you choose a value for RB and then you calculate RA. It's up to you. Then you pick a value for R, and then you know N from here. You just chose the value for R. You know the frequency, so you calculate the value of the capacitor. Okay, or you choose the value of the capacitor and calculate the value of the resistor. Any of those options are suitable for me. And then you draw the diagram.
Wow, you explain it. It's like so simple there.
Yeah, well, everything is given. Funnily enough, this question gives you everything that you need. You don't have to remember anything. The output is given by 4 over F is given by N over 4RC. So that is this here. So you need to find out N. What is N? N, that's the only thing you have to remember. N is plus or minus VSAT over, I shouldn't put that there. Is VSAT over the V upper threshold. That is this one. So VSAT divided by that. All right.
Mm-hmm.
Okay. VSAT now, they're given VCC. So you have to make a little assumption for me. Do I assume that VSAT is the same as VCC? If you do, say so. Do I assume that VSAT is a little bit less than VCC, like a 1 volt or 2 volt less than VCC? Say that. And then once you do that, that allows you to calculate N, right? And once you calculate N now, everything else is here. You're given the relationship between RA and RB and N. So you could calculate both of them. You pick one and calculate the other one. And then same thing for the resistor and the capacitor. Pick one and calculate the other one. And I get 12 marks here.
Stupid question. Which is the second op-amp that deals with the triangular waveform, and the first one deals with the square wave?
No, it's the other way around. This is the integrator
okay.
here. Notice because the capacitor. This is the integrator here.
Mm-hmm.
So the output here is the triangle wave. This is the one that giving these steps, which is the square wave. Right? Oops. Yeah.
Yeah.
The first op-amp is the output of the first op-amp. That is where the triangle wave is coming from. If you take the output
okay,
here,
I understand. I didn't see V out by the capacitor, like out of the first.
Yeah. Watch the diagram carefully. All right? But it is straight from the nodes.
Mm.
Okay. All right, and then the last question, well, we didn't do all pass filters, but this kind of thing. If I were to ask you the main types of filters, you should be able to do that very easy. What are the main types of filters that we have?
I know high pass filter, low pass filter, I think band pass filter. I think that's all I could remember offhand.
Okay, well, easy enough. Watch. A low pass filter, the ideal response is that it passes low frequencies, right?
Yep.
The high pass filter, I'm doing all on one diagram. The high pass filter is the opposite. It passes, it starts at some cutoff frequency and will pass everything here. Yeah, that's a high pass. So the low pass is in purple, the high pass is in red. So if you combine the two of them now, you have, if I combine the purple and the red as it is, I'm going to get a filter that is going to basically pass this, not pass that, and pass that. In other words, what does this look like?
A trough.
Right, or a notch.
Oh yes, notch
Right?
filter.
Notch filter, or the proper name for it, a band stop, because stopping everything in this band. And then the other one is, if I take the filter, if I take the characteristics here, so I do this, and if I have a high pass filter that does this, remember, high pass filter starts at some frequency and passes everything above that. And if I combine that with just let me get a good color here, with a low pass filter, which passes everything and stops, passes low frequencies and stops everything above there. If I combine those two together, then I get a filter that does this.
You get the band pass filter like
Right.
was used in the radios.
Exactly. So it will allow this set of frequencies to pass, right, but reject everything outside. So this is your band pass. Right? So those are the four types here. Band stop, actually on this type, they also call this, because this is band pass, they sometimes call this filter on this side a band reject as well. So all three, notch filter, band stop, band pass. So those are the four types, right? And the characteristics are there. So even, so that's an easy thing, although we basically concentrated on low pass and high pass filters in our discussion, but you can mix them and match them to get the band pass and band stop. It wasn't part of what we did, but you could understand fairly easily what it is, right? And this now is a particular type that we didn't discuss. It is not part of our syllabus this time. Something called the all-pass filter. An all-pass filter is a strange thing in that it passes the frequency, but what it does, it changes the phase. You remember us talking a lot about phase in when we did board plots and the like. Sometimes you want to change the phase of a signal, but leave the rest of the signal untouched. Phase is what changes things like the colors in videos or the bass treble arrangement in audio signals. So it could change our voice, or it could change our, how something sounds by passing the signal, but changing the phase relationships. We didn't talk about it, but this is what that type of filter does. The analysis is in the solutions there. It's basic circuit theory. So you could just see, just you know, if you have to analyze it, how to go about doing the analysis. okay? But it is not not part, oops, not part of what we did. Of this, right? So that is easy. So that we have spent the couple of weeks basically reviewing the course on all of the topics that we covered: oscillators, op-amp applications, power supplies, including protection circuits, feedback amplifiers, op-amp applications, the precision rectifiers, the other one that we spoke about, and then the waveform generators. All right, and this was just the response to the filters, and we did talk a little bit about low pass and band pass filters as well. All right, so going forward from here, I'll go back to and see if there were any things, if you want any specific topics now, just for us to go over, because the rest of the time now is really to be spent on you doing the questions. We have solutions here to spend. We have some other past paper questions to do the questions, to time yourself doing those questions now and see where you're getting stuck, and what else you need explanations and clarifications for. So at this point in time, it is really kind of handing it back over to you all now to let me know in terms of things that you might need some extra explanations on or clarifications on, and I could prepare like how I'm trying to do that one with the rectifier thing, just to clarify that, but similar things. All right, I put up the Google Sheet, but nobody put up anything. But now is the time to do it, because it's really up to you now. We've gone through most of the material again, and the question is for you. Well, sorry, your task now is to do questions and see where you got stuck, or where extra time is being taken up to do the work, or what else you need explanations on. Yeah. Right. So question. Let me hear it. You have to tell me now and let me know, and I could prepare accordingly. So if you tell me like for now that we have the like for Friday's class, for instance, you have to go through some material here. You have the other question papers to go through as well. To start going through that, and or tell me what you still need some explanations on. So you have to tell me that between now and Friday. If you use the Google Sheet, put up whatever it is, and I'll spend the time explaining the things and clarifying or explaining answers that you have that maybe not making sense, and so on. Right? Somebody I think it's what is had put the question in the chat. Kamaraj, you had put something right on the YouTube channel. He had put a question about the calculating the feedback voltage for a feedback amplifier. Why I'd use the particular formula, and it actually referred to a slide in the previous lecture. So I'd answered it there. But it's those kind of things. If you're going through and something not making sense, why was something done? Let me know, and I'll take it up in class and explain it for everybody again. Yeah. Okay.
Yeah.
All right. So well, without further ado, I think that's it for today. And well, it's over to you. All right. So you have to tell me now how we're going to spend the rest of the time. You have revision to do. Time yourself on the questions, like I said. If I come up with additional questions and so on, I could give you it to do, and see how well you do it. And maybe now might be a good time too, if you haven't done so, to go over the last year's paper again now, and try and see how much you remember, and how much you're able to get done in the times for each question, and so on. and let me know again where the issues might be. Yeah.
Okay, will do, sir. One thing that was a little bit complex that I had now reached the monostable multi-vibrator. And it was a little bit complex, as I would say, and I think I would add that to the topic of things to explain.
Okay, so go on. You should still have the link for the Google Doc. So put it inside of there for me. Monostable multivibrators. Yeah, put that in there. Right, and I'll take the topics in order as I see them. I'll take the topics in order and discuss it the next time we meet.
Okay, will do, sir. Thanks.
All right.